So let's get started. So today my topic is what silicon photonics can do for a wide range of telecom and data communication, particularly data center applications. In general, there's actually fairly high expectation from the market for silicon photonics, and I'm just citing two of the industrial forecasts here. One is from Light Counting, as a well-known forecast firm, particularly looking at the transceivers. In this particular chart, basically showing what is the percentage gain over the next few years if you're looking at silicon photonics as a percentage share of the total transceiver demand. So what they are forecasting is today is roughly about 25%, mostly focused on data center and also some coherent transceiver based on silicon photonics. In the next few years, with the increase of overall transceiver demand, the silicon photonic content actually going to continue to climb and grow. And in this case, they are forecasting 50% of shares will be based on silicon photonics, and this is by 2026. And the total value of that will be over $10 billion. There's another market forecast firm, Yale. They actually forecast in silicon photonic dies. So this is a different way to look at the market. One is from transceiver, the other one is die sales. And they're estimating about $1.1 billion worth by 2026. And in my presentation, I'd like to show that even these forecasts probably underestimate some of the important areas. For example, we're very much focused on early commercialization of germanium on silicon, PD and APD receivers, and these probably not counted by these market forecasts. Just a quick introduction about SiFotonics. The company is founded actually quite early in 2007. As one of the pioneering research of silicon photonics at MIT, the founders actually pioneered the silicon photonic development and commercialization, which is important to push these early silicon photonic development into productization and commercialization. Over the years, SiFotonics actually developed a slightly different business model. If you're looking at the foundry models, we actually use so-called IDM Light, which means we actually had a vertical control of the silicon photonic fab itself, but still using commercial CMOS foundry as a service. So this allows us to actually have fairly efficient R&D iteration models, but also have good control of the silicon photonic process itself. From our earlier development, we actually developed a few industry-leading platforms. One is germanium silicon PD and APD. This is actually fundamental on the detector side. And then coherent PICs with fully integrated IQ modulators and integrated receivers. Then last one is recently it's really grow fast. It's with PAM4-based MCM modulators and PICs for data center applications. Recently, based on these platforms, we actually pioneer a few industry standards with industry colleagues, particularly 100G ER1. And we also offer a few O-band WDM with these single channel 100G. And then 400G ER4 is coming. And again, these fundamental building block requires very advanced high sensitivity APD. So we actually use germanium silicon APD as one of the key enabler for this. And we've done this through industry standardization like 100G lambda MSA. Over the last few years, we actually continue to introduce a product into the market. Again, start with the bottom up. We started with germanium silicon PD and PD arrays. These are actually widely deployed in the telecom and datacom applications. And then we introduced germanium silicon APDs, which is really advancing the sensitivity at a increasing higher speed. So we've gone through 10 gig, 25 gigabaud, and then 53 gigabaud. On the coherent side, we start with integrated receivers on silicon photonic platform, and then we are introducing fully integrated ICTR, basically fully integrated modulator and receiver in one single chip. Now we are starting to introduce 800 gig integrated coherent circuit receiver. On the PAM4 front, we introduced the DR4 last year. Now we start to look at the 800 gig DR8. So from germanium on silicon PD, this is actually widely deployed. Many of you may not know, but it's already in 5G front haul and data center applications. Germanium silicon PD actually already winning market share for fairly broad applications. And this is based on a CMOS 8-inch wafer, and this is actually give you very good performance and competitive cost advantage. And just to give you a benchmark, we actually ship already 200 billion device hours. You can actually calculate. This is actually over very large numbers, tens of millions of these chips shipped. So this is actually widely used in like 5G front haul, for example. And in data center, you actually don't know, but actually this is already being deployed in many of these different applications like 100G PSM4, CWDM4, 200G FR4, now increasingly start to get into 400G DR4, 400G FR4, and now you are getting these 800 gig starting to get deployed in the market. Then if you're looking at APD, this is actually fundamental building block to the next generation PON applications because they all require very high link budget. If you're looking at the APD, we actually deploy in the field. This is also up to 20 billion device hours. So this is actually all very large numbers. You are talking about maybe 1.5 million of these chips actually shipped and deployed. The 25GS PON is coming, and then there's a 50G PON also coming. So you can actually see the sensitivity requirement like 25GS PON N2 class actually require 31 dB link budget, and the RF sensitivity actually require minus 26.5 dBm. So these are very high sensitivity requirements on the receivers. 50G PON as well. If you're looking at the RF sensitivity, it goes down to minus 24 dBm in the 50 gigabaud NRZ mode. Here, just to give you an example, we're showing one of the representative 25G NRZ APD performance. You can see if you're looking at down to 1E minus 2, the BR correction levels, we have quite a few dB of link budget margin. Then increasing the speed, going up to 53 gigabaud, you actually allow us to introduce this new class of 100G per lane solutions for telecom service provider as well as a data center interconnects. This class of APD actually allow you to have 5 to 6 dB extra gain compared to pin dial, and this is allow you to extend the distance. So we basically can now replace traditional 100G 4x25, actually now migrating over to 100G per lane optics. Then the electrical host interface can then migrate over to 2x50 or 100G without doing any reverse gearbox. And just give you some of the representative of product actually enabled by this high baud rate APD. So one of the class of product is called 100G ER1. Basically, single lane can now cover 40 kilometers. And then you can also go smaller, not only longer distance, but go smaller. So you can actually use these much smaller SFP form factor. Right now, we are actually already introduced to the market in the SFP 5060D, and next, you start to see SFP 112 in the marketplace. Since you're already doing the single lane 100G, now you can introduce easily O-band WDM. So you can actually now start to see this kind of product like 8 wavelengths with O-band WDM and go extend the distance. And then increasingly, you can also increase the total aggregate capacity per module. You can then introduce this 400G ER4, basically using 4 lanes of these 100G, but going longer distance, like 30 to 40 kilometers. Here, just to give you example of the performance on these SRP56DD 100G ER1 modules. Thanks to the flexibility of the DSP, you can actually set the operation mode to 53 gigabaud PAM4. This is 100G per lane. But then you can also do like 26 gigabaud PAM4, which is really 50G format. And then you can also do 51.6G NRZ and then 25G NRZ. So in this chart, you basically use one single transceiver can showcase what the transceiver sensitivity is for receivers. On the extended distance part, you can actually use silicon photonic modulators, take advantage of the low chirp property. So you can actually have fairly good dispersion tolerance. In this case, you can basically support the SPED defined by 100G ER1 with a very low T.Q penalty at the limit from -60 to plus 35, 37 or so dispersion range. And this is published last year. And then if you're looking at the data center application in particular, you can actually construct N by 100G with the industry migration now at 4 by 100G, but now next going to go to 8 by 100G, and people already start to talk about 16 by 100G for 1.6T with silicon photonics. And then if you're looking at the next generation, we already heard a few speakers talking about 200G PAM4. This is going to start to happen as well. So silicon photonics is demonstrating its feasibility to support that. In the picture here, you actually can see M by 100G silicon photon chipset. In this case, we're doing 4 by 100G in this example. On this, the upper side is Mach-Zehnder modulator arrays, and lower part is actually germanium silicon PD arrays. And we can construct this into different solutions for end users. For example, we construct this a DR4 silicon photonic engine. The module maker can actually use this to pair it up with DSP to make a DR4 transceiver. And in this particular case, we basically put all the silicon photonics on the chip on board configuration, so you can build the whole DR4 transceivers as an example. Going to 200 gig PAM4, we are demonstrating that by pairing up properly with the electronic driver IC, you can actually get fairly good bandwidth. In this case, now we are pushing over close to 60 gigahertz bandwidth, and you can start to get 200 gig PAM4 eye diagram. So there's still some work to do in this. Obviously, we like to push a little bit even more to 70 gigahertz, but this is starting of that journey of 200 gig PAM4. On the receiver end, using the germanium silicon waveguide PD, you can actually push the bandwidth to very wide. You can see well beyond 70 gigahertz here. So I think on the feasibility side, silicon photonics also started to prepare for this next generation product for data center. On this chart, we actually now start to look at the wider application for silicon photonic coherent. And this is to show Signal AI looking at the recent progress on 400 gig ZR and ZR plus pluggables. They're showing this year alone probably going to hit about 200K. So this is industry migration now going really to pluggable coherent transceivers. And recently you also see some announcement from like 26 EVA about 100 gig ZR opportunity for access aggregations. So silicon photonics is becoming really the mainstream building block. We contributed to that. If you're looking at our shipments, already hitting like 1 billion device hours. So these are not, again, small numbers. This is actually represent a decent market share of silicon photonic-based transceiver. And if you're looking at industry roadmap, we also started here talking about coherent light, increasingly going for even shorter distance. And look at the pictures here. We're basically showing this is just an integrated receiver alone. And this chip actually representing a fully integrated 4-lane modulators, IQ modulators, and receiver in one chip. So these chips actually go into so-called COSA. This is actually a coherent optical subassembly people use to construct their transceivers. There's a picture view showing using this COSA or even use chip on board platform, you can actually construct coherent transceivers going forward with tunable laser and DSP. This is a chart we are showing the industry roadmap with silicon photonics, and this is doing the two axes showing the bar rate going to the right and then a distance going up. For lower bar rate, certainly the IMDD configuration can adequately go reasonable distance like 10 kilometer up to 30 kilometer-ish. And then if you're going to going to higher bar rate, the covering distance basically need to be helped. So here, germanium silicon APD really helping to bridge that gap between IMDD with the pin diode, but using a coherent detection. So germanium APD actually covering the whole landscape using direct detection going longer distance. So we actually start to cover, for example, 40 kilometer with 100 G ER1, and then 400 G ER4 covering 30 kilometers using APD. So you don't have to go coherent, going 53 gigabaud until maybe going long distance like ZR class. So if you're going forward further, going to 100 gigabaud, coherent detection will start to cover shorter distance. So there's a good industry discussion and debate going actually over in 100 gigabaud, what can be covered by IMDD versus coherent. But suffice to say, silicon photonics will cover both the coherent detection, but also IMDD with both pin diode and APD. So I think overall, just want to give you the impression that silicon photonics not only just cover very well publicized data center application, but really you can cover the whole landscape of telco application as well. Here just to give you a more pictorial view of what technology actually can be covered by the left side, really access applications, fiber to the home, and 5G wireless front haul, back haul, and then also enterprise for business network. You can actually find footprint of silicon photonics, PD-APD receivers, or if you want to go longer distance, you use a combination of APD or coherent for the ZR class type of product. And then in the metro core, most likely going to be silicon photonics based 400G ZR or even ZR plus product. And then going to data center, you actually see the PAM4 based M by 100G PAM4 going to cover pretty well a few generation of product. And then we'll start to see the 200G PAM4 coming in the next few years. And if you're looking at data center connections, like DCI, you will see the 400G ZR really start to get deployed. And then we are talking about next generation, even coherent light, start to cover like campus networking type of applications. And in summary, here just to put everything together, you can see in the telecom side, you actually start to see good applications for germanium silicon, PD, APDs, and then on the coherent, you really start to see good coverage on 400 gig ZR and go to 100 gig ZR access. And then even from roadmap point of view, you start to see 10 kilometer coherent light. And then it's well published that silicon photonics really start to see and become a mainstream going from 100 gig, 400 gig, 800 gig migrations over the next generations. And we also mentioned the 200 gig will start to become feasible as well. So thank you very much for your participation and attention.
Thank you. Thank you. So any question from the audience? So any questions? No? So Ran, can you go to your slides talking about the applications? Yeah, from this side, right? Try to understand. For example, I think for the if we're talking about the base stations, right? The distance normally short. Do you think the coherent really need there, or you think it's like a 30 kilometer, 40 kilometers, pretty much is okay with MDD? Because you talk a lot with MDD, yeah.
Yeah. So particularly talking about base stations. So here, I'm not actually advocating the coherent going to go there, because this is an area I think can be addressed by MDD. For example, we are using one example here is even you use 100 gig, you can actually go cover 20 kilometer distance with 8 wavelengths here. So this is MDD is adequate for that particular applications. But for the backhaul aggregation, I think there you will start to see the combination of MDD and coherent. So coherent probably going to see key play in aggregation over 40 to 80 kilometers. So this is the range I think you start to see more aggregation, but not necessarily go to like directly to the cell tower.
Okay, thank you, Ran. So any question from the audience? If not, then move on to the next speaker.